So we're at a really cool stage of actually having a pattern to potentially make sense of the structural universe that contains all the transforms or the exact identities of the constants of nature we currently have. So that's my intro sentence, and I want to walk back way up. I want to go through the process by which we got to where we are, so that if we're wrong, everyone's very, very empowered to come up with a different answer, using the process or whatever. But I want to be clear about what the process was. Okay, so the first step is, I suspect, fastest way to tell this, the first step is a years long process of learning ways of investigating the reality around you. Okay, and I would recommend the best, fastest story to carry you through that would be learning courses in physics, because there's lots of ways to look into the world and then interpret what's going on. But physics is the discipline that uses measurement to do that. And measurement's always going to be better than any interpretation our brains just intrinsically try to make a story out of it. So the goal here is to try to put together a story that accounts for all the actual measurements we've made through our whole history of physics, right, or our whole history of humans so far, to identify the built-in features that are fixed into reality. So that's very clearly statements here. We are assuming the constants of nature are accurate measurements of built-in features allowed in physics. Okay, so we're taking that as the starting position. And now what we're trying to do is we're trying to come up with any sort of logical model, a geometric-based structure. It has to have explicitly specified logic, and we want to find the simplest possible logical model that contains and explains all of those features. Okay, if that simplest model has other features, cool. Whatever happens, the simplest one that can contain the features we know are real. we need to, at minimum, account for all of those. But by account, we really mean deeply. You can't just account for something by just reproducing it. That reproduction needs to be some sort of action, some sort of story, some sort of insight to the structure of what's going on, not just, you got it right. That's what quantum mechanics does, right? It gets it right, in a way, like statistically. But it didn't really give you insight to the structure of what was getting it right. So we're trying to get past that. And we're not starting out with an intuition of exactly what the universe is supposed to be. I mean, we've all done that. I've done that. I wrote a whole book to try to fine-tune my intuition of what it must be and fine-tune my collection of the details I have to keep track of and account for. Okay, but at the end of that book, I ran into a wall. The main thing I tried to focus on was trying to visually, or without reducing dimensions, track the action of gravity, right? That we have exact equations from general relativity for what gravity is. And I wanted to not have to take a slice and then understand those equations a slice at a time. I wanted to find some way to more richly understand them. And the method for doing that was to introduce a notion in which space-time itself, the metric itself by which everything's being compared, is actually quantized, so that there are other degrees of freedom that allow the metric to mix, right? There's a whole bunch of bubbles that can move around, but it gives you available density gradients and all the fluid actions that we characterize in fluid mechanics. Okay, the problem was that although this separation of the metric itself gave us density gradients, which actually perfectly map to the logic of warp spacetime, they didn't give us an explanation in the end. Once we were mapping spacetime's warping curvature, that mapping didn't then give us a next step of insight that said, and now I know why the boundaries we made up or imposed on the situation in order to have that kind of structure exist. You follow me? So we got to a position where we found, if we come up with a condition where we impose this different kind of metric of spacetime, one that's quantized and has parts that can all mix about and so on, then we can reproduce the same sort of effect. But the goal, when you have a model like that, when you have so much you're just assuming, is that you don't really believe the model until you kind of tweak it to make the fit that you were looking for. But that tweaking and that fitting should then automatically be fit to a whole bunch of other parameters you weren't actually trying to tweak it to. So that's the situation I ended up in. It didn't give me any insights for how quantum mechanics would be coming out of the same sort of model. So it was just fine-tuned. It wasn't powerfully revealing. So what we're going to do is instead, we're going to back up and not assume whatever model you're currently assuming, what the space is infinite, or that it's spherical and infinite or finite, or cubic and infinite or finite. Those are common visions. We're not going to assume a certain geometry. What we're trying to do is focus on the measured transforms, or the measured built-in facts of reality, and find some way to make sense of them. So first step is to list them, or to become aware of them. So the physics track tunes you into the investigation humans have had so far, using measurements to look into reality in new ways. Look into reality in ways beyond what you can do just with your hands and your eyes, using tools to look further into the structure and precision of what's going on. Okay, so in that process, people have discovered that they can model actions using equations, and some of those equations, most of those equations, have strange scaling factors that relate things to each other, different parameters like as time or length and space, right, to each other, but with huge scalings. So it's not a one-to-one conversion, but there's a conversion. Okay, so the first thing to notice is that there are conversions between the different parameters of reality. So I guess even before that, we need to notice that physics gives us 5 dimensions of measure, 5 different bases, different actions by which we can make our reference in a story already. So that's a starting position. Those measures, those 5 kinds, time, space or length, charge, temperature, and mass. All right. This is very, very fast, but the major point here is that these 5 bases, these 5 dimensions, form a network of logic that account for all the transforms and exchanges we've found or just seen so far in physics. The things we're trying to account for. We're not trying to account for ones we haven't seen yet. Okay, so all of them. That's a really amazing thing. You can reduce every statement in physics to statements that involve either no dimensions or mixtures or sets of these 5. That's it. Okay, so there's 5 ways to make unique measurement in the world, or 5 unique dimensions. The next big step, and it took a lot of time to go from there to this next big step, is that there are limits built in to the world, or what? Well, I want to be kind of clear about this. These aren't limits built into an infinite extending universe that just exists without logic built into it, right? That's not what we're talking about. These limits are found directly from looking at the constants of nature and comparing them and seeing that if all the constants of nature are true statements, then they imply cutoffs for some reason. There's no explanation there for why, but they imply cutoffs to these 5 boundaries. So in the constants of nature themselves, we find the Planck time, but not to perfect precision. We don't even know the constants of nature to perfect precision. But strangely, we get the Planck time to way less precision than we know the constants. We also get the Planck length, we get the Planck charge, we get the Planck temperature with a capital T, and the Planck mass. All right, so now we have a story in physics that's revealed 5 different dimensions by which we logic things together. And we have a bunch of constants of nature. It turns out 288 constants of nature. And that's about as far as we can go with the data set, the facts that we have to account for, other than the equations are already currently known that connect some of these parts, right? E equals mc squared, the list of equations that physics has written down that hold at least, well, some of those equations we know hold to 7 significant digits and some of them hold to 14, but still, those are the equations that we need to connect things with. Okay, that's the starting part. I see this as we've been given, well, it took a lot of work to get to this point, but what this point represents is we have the box of puzzle pieces. It's a puzzle that has 288 pieces, and we only know that. We can look at each of these pieces, we can see the measurements, and maybe some pieces are fuzzy. For some reason, you just can't focus so well on them, right? Because we only know them to 3 significant digits, and some we know it to 14. Okay, so there's a problem in the box. The puzzle pieces don't have all really sharp edges. Like some of them have been faded for us. We don't know exactly what they look like, but we do know the number of pieces. So the first thing we want to do is we want to organize the contents of the mystery, right? The certain puzzle pieces, usually when you get a puzzle like that, you know there's going to be an edge, a boundary, right? So you want to separate the boundary pieces from the non-boundary pieces, right? Separate the like things. What do we do in this case to do that? Well, we have 5 base dimensions and 5 limits to those dimensions and 288 constants. Well, to look at these things, we only have certain content. There's, for example, the famous speed of light. It comes in a string of digits. So we assume this is exact. So I'll just put a bar like this to let you know we're claiming this is exact in code data right now. Okay, times 10 to the 8 meters per second. The meters per second are a very explicit, important part of the claim of the constant of nature. It's a constant ratio or transform between meters and seconds. That's what it is. That's what it's doing. It's not a constant of nature if we change the bases. It's equivalent, since we're just talking about a small dimensional relation here. You can talk about the speed of light in terms of feet, but we're not talking about connections that are logic down to the minimal possible forms if we go out of the bases that they're in. Okay, that's an important thing. We've recognized in physics that there are important bases. Important because what? Who picked them? Who made them important? Atoms. This is just the logic of atoms. The whole thing we're figuring out is what's built into what atoms can do. There's a certain set of kinds of atoms, and there's a certain amount of exchanges between the atoms. And when those exchanges happen, transformations happen each time. But it's not an infinite set. Okay, so we have in this, we have a symbol we use to represent it, but the actual data is just the string of digits. We normalize them all to have a number and then decimal, so this is scientific notation, and then we show you how many decimals off shifts by the power, okay? But the dimensions are important, the power is important, and the string of digits are specifically important. If we're gonna make sense of the mystery, we have to collect that data for all 288 data points and for our limits. This is a problem actually on this side. Okay, we have the data points. Yeah, the ones with less digits are more problematic than the ones with bigger digits because you have some fuzziness there to make sense of. But these guys are all fuzzy in comparison to these, in comparison to most of those. We know them to 5 to 7 digits when we know these out to 14. The best ones out to 14, but 10 is very common, okay? All right, so the question is why? Why would we only have insight to the limits of the boundaries at 5 to 7 significant digits when we know things 10 to 14 out here? When we extract them from things that we know to 10 to 14 significant digits. So as you do that through all the constants in nature backwards, you have the data points and you look at the relationships between them, trying to reduce to the simplest possible relationships like a single measure of time or a single measure of space, right? To understand these limits more precisely. You find out that, first of all, you get a more clear data set that after 7 significant digits, there's changes every time. You can reproduce the same number for first 5 to 7, and then it'll be different if you started with a different set of constants to get there. Okay, second thing is that if you try to go forwards, you know, these guys have to have actual answers. There's real values for the ones we don't know in the digits. So what I can do is say, well, we know we're only telling the story out to 14 digits. I know these out to 5 or 7 there. So let's make up the rest of the digits and cycle it through all the possible ones. You can, in a computer, tell it to literally try all the options for the rest of the digits being the value for that out to 14 digits. It's not that hard. It's just 14 digits, okay? And what are you going to do with it? Well, then you're going to take each of those possible values for the Planck time and compare it to each of the possible values for the Planck length when building the speed of light, because the speed of light has length over time in it, okay? And you're trying to check in every relationship between all the constants, do I get a point where this 7-digit transformation, this things changing at 7 digits doesn't happen? That would be the ideal best place to find something, right? That's what my search was. Well, it turns out it doesn't. And you can convince yourself of that because we're only going to 14 significant digits. It's a very finite set and you can computer check them all. It turns out no matter what the numbers are, what are the rest of the digits for these 5 boundaries, the rule that things change when they connect at 7 significant digits is built in. So what I did after doing all those checks, I decided to write this rule down and say, there's 2 parts then. There's some sort of geometric external action on some sort of boundaries. And then there's a smaller part that comes in at the 7th significant digit for an internal action and some internal boundaries, which we use this symbol for. It's always the same internal boundaries if it's the same system. Lots of different external expressions, but since they all twist around the inside, they're all going to have the same internal boundaries they turn around on. But they can use different geometric actions to do it. They can use a lemniscate, they can use a circle, they can use whatever shape they actually do use. But this is now a prescription for how to tear apart a two-part system made of certain kinds of boundaries. And if we're applying it just to the Planck boundaries, then this is a simple bilinear construction for putting together an action or a transform for every single constant of nature. Put it like that, for every constant of nature. Technically, in a 5-base system, you expect that you should be able to arrange the bases in some configuration that pinches out any one of them. So you should be able to pinch out time, like in a black hole, right? Pinch out space or pinch out charge, at least at a point, okay, in the geometry where they can't express. Okay.
What's the maximum number of expressed dimensions for a single constant?
4 at a time.
So it's never all 5?
No.
That's interesting.
Yeah. Yeah, so perhaps that's the same thing I was just saying. One of them's pinched out each time. Okay, so we're just trying to explore the data points and investigate, right? We don't really know where this is going to lead yet. And we're taking the clue because we checked a ginormous set of data points and found that it doesn't really matter what we pick as the digits here. That thing that we were trying to get rid of, that, well, it changes at 7 digits. I want to know what the actual digits are, not, I get it to not change. You can't. That's built in. So that means your next assumption that's reasonable here is, all right, that tells us that if we're actually constructing things from Planck constants, then we have to be doing it in 2 parts. Now that we've got this rule, we have to go through all the work to try to tear apart each of these constants in nature in terms of it. I'll let you know where the errors potentially could come in this process, so as we go. So the first thing is you set it equal to 1 constant at a time. And then you set, let's ignore the smaller part, so we can pretend this is a 0 right now. Okay, the whole thing, or just pretend the whole thing is just 1. And we set the boundaries of the external arrangement here equal to the dimensions of the constant. So in this case, the dimensions are just meters per second. So if we're going to have speed of light, it's going to be equal to some number we don't know yet, external, times by the boundaries. The boundaries are going to be meters per second. What's the boundary of meters? Planck. And the boundary of seconds is the Planck time. All right, so we've got the first part of our construction. This part only should come in roughly at 7 significant digits. So we should be able to get the answer, the first 7 digits, to tell us what this guy should be here. Okay, great. So when we do that, we found out that this number is 1. Okay, another example of that. So I don't even need to write it in this case because we assume the 1's right. And now we bring back the second part. Internal and boundaries. See, piece by piece now, we can exactly find the numeric value and error bars on what this guy should be. And then we can go search using Wolfram Alpha, the same way we searched here actually, using Wolfram Alpha, to check what sort of geometric simple things represent that. Now here's where the error can come in. If you find something beautiful and simple, you write it down, you might as a human say, aha, I found the truth. I found something that's definitely true. You have to keep track of your error bars. There might be more than one thing that's an option. So we got to stay a little, what we find here, you keep a list, right? And you keep all the ones that you can, all the ones that match, and also down here, but 1 was a pretty dead giveaway. It's hard to beat that. All right, so that's, if you have less measurement data points, if we have less digits in the actual data point to begin with, then your confidence of this end piece will be even less. Note, though, it doesn't change really much the front one. You're always going to get it. Okay, so the confidence on the right-hand side goes down if you have less digits, of course, or if you have more beautiful things that could satisfy it. What are you going to do about that? How would you decide between them? Well, my method was to then just keep this as a record, move on to the next constant and do the same process, and find the best list. And if I happen to find two matches, it's, oh, if those are both this one and this one, then I got a pattern even between two constants now, and keep going and keep going and keep going. And if they can find more things that can pattern up into bigger groups using less constants to do it, I have more confidence in it. Now remember, this doesn't actually make it right. It gives me more confidence in it. I have to be willing to still change and go back and forth and keep checking. But this is our investigation, our puzzle, our attempt to put the puzzles together. First way we're doing it is we're pulling apart into universal constructive pieces. And we're trying to get the minimal set of pieces that we can do it with. Okay. Let me do a little interlude here, or side note, for those who have been doing this for a while. It turns out after we finish the entire process, this construction here in the entire set of 288 constants ends up using, let's start with this one, 44 unique parameters. This one uses 35 unique parameters. And between those two, these are both actions. These are geometric parameters like pi or the lambda scale constant, stuff like that. Between the two of them, they share 18 of the same ones. Very interesting to me. I'll show you why in a second. And it turns out that the number of unique boundaries that can be put in this position in the whole set of constants in nature is 32. Okay. Let me mention why that's interesting. This number has a scale of 10 to the negative 44. This one has a scale of 10 to the negative 35. This one has a scale of 10 to the negative 18. And this one has a scale of 10 to the positive 32. This one has a scale of 10 to the negative 8. Pattern-wise, the unique number of parameters for each of this constructive rule for putting things together, for each piece in that constructive rule, are matching the powers of the Planck constants. I'll also throw in another side note for fun. The volume equation for the 24-dimensional unit hypersphere turns out to be 4 pi over 5 factorial, which is 120, times by 4 pi over derangements of 5, which is 54, okay, and times by 4 pi over 35, 4 pi over 18, 32, and over 8. 4, 3, 2, 1. The same division construction defines the structure from here out, the divisors of that system too. Okay, I'm taking that as a strong clue, but still, all of this should be taken as clues. We're trying to find the actual reality, the story of reality that most simply structures together the rules. Okay.
Isn't that also the same density as like the Leech lattice?
Yeah, it's the same thing actually. Density, the Leech lattice, very famous structure in geometry, very, very beautiful. Everything fits together perfectly with no gaps. It's just very beautiful structure. We have this one rule, binomial constructive rule, right? That things are made up of two parts, an outside part and an inside part, but that they're connected, they're fit together. This is just analogous, this is perfectly analogous to the way that Newton started to pairwise set the rules to things to get calculus, right? And broke it into two sets of things that are connected. So far, all we're doing is we're tearing apart for how things fit together in terms of the Planck constant boundaries and their actions. But it turns out a lot of these actions involve geometric numbers that relate to the fine structure constant. Okay, so we need to get some little insight on the fine structure constant. And we really lucked out here. De Vries noticed that there was a simple way to relate the fine structure constant, at least to high precision. Not perfectly, but more digits than the way people had found before, using just pi and e. Only pi and e, some of our favorite geometric constants. Okay, so this kind of got me interested, not just kind of. I was already spending years looking for a way to make sense of the fine structure constant, and there was nothing. There was literally nothing. There wasn't even a proposal that partially made sense of it in any way for me at all. So I was looking for approximations and hoping that I could find some sort of algebraic form that gets us there, and therefore I could look into the form for more clues about what's going on. Well, it turned out that if I rewrote his equation slightly, this point, we have no idea why this is working. We're just noticing that this is basically the form that I could rewrite this equation to. When I did this, I got 8 significant digits of the fine structure concept, which we knew at 11 at the time. So not good enough, but actually a lot closer than anybody else. And more importantly, a lot closer by using something that so far we've only put pi's, and you can transform this to an e, okay? An e's or i's. Pi's and i's are both beautiful, beautiful things now. Okay, but I needed an algebraic statement like this, something I can look into, something I can ask about its structure and get more information. But it needed to actually characterize the fine structure constant. So close, so close. We almost got it, right? So I just wanted to check, what if I used x already, y? It's some small difference here. I want to know how far off is this from getting us to the right number, okay? To do that now, I don't know y. And then instead of solving for x, I'm going to go ahead and put in the fine structure constant here. Actually, I'm going to put in the square root of the fine structure constant here, here, and here. The measured number with the error bars, okay, of the current time. Okay, and then you get a value with error bars for the y, what it must be. So meaning this equation must be modified by the value of that in order to exactly get, at least to your current measurement, the fine structure constant. And it turns out that the y was of the magnitude, so we'll call it the normalized Planck mass. The scale that represents the relationship between the boundary of mass and the projective base of mass, okay, that relationship was the same scale that made this thing work. Does it make it right? No, we're investigating, we're following a story, we're trying to make sense of it, right? But this is a great clue why? Because in projective geometry, hyperbolic spaces, so the core like this, the double cone, and the single sheeted hyperboloid, the double-sheeted hyperboloid, we can describe hyperbolic spaces, which you might be familiar with in physics, of many, many, many kinds. In fact, if you believe that it's not discrete, then an infinite number of kinds by picking different distances between these two sheets. You can see it changes the angle of the cone, it punches this guy, it changes the whole relationship, but the same relationships are still built in. They just have different scales in which they're holding, okay?
Could you just go over like how we could slice up the conic?
Oh, sure. So this conic structure, if you take a plane now and imagine just cutting through it, you have to imagine the 3D-ness that was implied here, okay? But if you cut through this way, right over through the cone, you get a circle, right? And if you go higher, you get a bigger circle. If you go lower, smaller and then bigger, right? It flips all the way down to 0 size in the center. Okay, if you change the angle of your cut to like this, and slice the cone. I'm just thinking about the cone right now. Then you get ellipses. In fact, you get all of them. So you go to hyperbolas and parabolas. So this structure reduced by a plane, the intersection of a plane and this structure gives you all of those forms. Circles of each size, ellipses, actually a double set of ellipses, a double set of circles, hyperbolas, which are already doubled, and parabolas. The thing that distinguishes this hyperbolic space from a different one is if this two-sheeted hyperboloid is closer or further away, that gap. And that's what this is representing. And we call that gap in hyperbolic spaces the mass gap. Okay, so I'm taking this as an even stronger clue because it turned out that the boundary of mass in relationship to the projection of mass literally defines the mass gap. Interesting. What does that mean? I don't know, but I couldn't think of a better answer than the mass gap being set by the Planck mass. So let's keep following. Now what happens? If we set that there, we get a different value for an exact value. Well, if you have an exact value for the Planck mass, you can then get an exact value to any digit you want for the fine structure constant. Okay, that was the goal. This is the guy that brought us here. But then, when we look into this form, we find it has 4 solutions. J1, J2, J3, and J4. J1 is the one we came here for, fine structure constant, but it comes with 3 other roots. It's a quadratic system that has 4 roots that are in relation to each other. And if you want to write down the relationships between these, we convert this into a true polynomial, so there's not an x in the bottom. So raise everything by power of x and just follow the Vieta relations. And we get our product of all four roots of this quadratic structure, where that one is the square root of the fine structure constant, is 2 pi. The sum, beautifully, gives us a balance by being 0. And the next thing we want to check, of course, is power sums, or the quadrants. So it has this very special name. So these are simple algebraic relationships you would check for any system. You take its roots, check the product of the roots, the sum of the roots, and the quadrants of the roots. And usually you get some crazy number that doesn't mean anything to you. In this case, we got 2 pi, 0, and negative 4 pi. And in fact, we can calculate any power of the roots. We got the recursive formula for all of them. And pi's show up all over the place. I mean, very beautiful structure, but the base set is the structure I want to focus on. This is a set that has a product, a sum, quadrants of 2 pi, 0, and negative 4 pi. 2 pi, 0, and negative 4 pi. Why would this be important? If you're looking ultimately for a transform logic for a system, the most beautiful transform logics that are available are the simple sets of cycles, right? So pi, or the simplest cycle, you might think of as the unit circle, or the next simplest being the unit lemniscate, right? Or you can think of the simplest ones, but pi is definitely in the list of simplest. Okay, we have a relationship, a transform relationship of the roots of the structure that give relationship, in the set, give relationship between a circle and a projective sphere. This is the surface area of sphere, and it's negative. This is just a circle, which is the belt around the sphere, you could say, right? There's one way of saying it. Okay. Now, we have a rule that we found from the constants of nature. We have a clue that we got from de Vries, okay, about algebraic structure that we actually modified just slightly to then get all the digits at the time. Side note there, we're now, the most recent one, 7 sigma in disagreement was Joe 1, okay, but not with all the rest of constants of nature. But at the time, within 1 point something, 2, 3, I can't remember, but within the 5 for sure.
It was literally within about 1 sigma, I think, and I think it might also be Hestus. The square root of alpha, the fine structure constant, wasn't that the way that Professor Pyman liked to think about it?
Yeah, he did. He said this is the one you should be focusing on, not the square, because, okay, well, let me back up. The reason we came to this, why? Because in trying to interpret this 2-part structure, we noticed that there were a lot of cases in which that guy is J1 or J1 squared, or J1 cubed, or J1 to the 4th, or J1 to the 7th, or J1 to the 11th. There's a lot of J1s that show up here. And sometimes just by themselves. Sometimes it's a 2 pi times J1 squared. Sometimes it's a 2 pi divided by J1 squared. But the J1s are all over the place in our set. So we needed to somehow we don't have a story currently in physics or in geometry, right? Anywhere for the J1s. That's what we're looking for. So here we've come to a story. We've nailed it to a story. Is it the right story? We don't know. But we finally nailed it to a story. And its roots are some of the most symmetric transforms in geometry. Got a really good start. Where do we go next?
Yeah.
Could you accidentally solve for which part of this? This one up here?
Yeah, no, it's accidentally solved for the 2 pi part. Like,
the way that equation is set up, no matter what you scale that y by, you will end up getting those roots, or at least when I investigated it. So in case you need it, but you're going to get different numbers, but that relationship, that 2 pi relationship will hold because it's literally built from e, that I to the I is a version of like e to the pi in some form.
The danger of finding what you're looking for. Okay. But it's invariant.
It's invariant, but there are versions that aren't. So since you brought that up, the cubic one, if you just go up 1 power, cube plus 2 cubed, 3 cubed, oops, 6 pi times a, where a is 1 over J1 plus 1 over J2 plus 1 over J3 plus 1 over J4.
It's a crazy equation.
Yeah, but it comes in rules, all the higher powers, A shows up over and over and over now, it simplifies it. Okay, but the point is wherever A comes in, I told you what A is, but wherever A comes into the structure, it isn't invariant, but via the A, right? So that is a good thing to notice, yeah. In our quadratic structure, our A is, this can all be thought of as a constant right here, right? This is A. Okay, and which means, literally, if you take 1 over Z1 plus 1 over Z2 plus 1 over Z3 plus 1 over Z4 and get the number, it will equal that. Okay, so it's a first rank distortion in our quadratic structure. First rank meaning it has a place where it's doing a distortion, it's adding an effect, but it has a lot of the connective structure that is not affected whatsoever by that, just some of it. Okay. Okay, so from this now I've got to test this structure, the only structure we've ever found, especially quadratic and beautiful, connected to the fine structure constant, to this rule, just these two rules alone. How do I do that? I tear apart every constant in nature according to this rule into actions and boundaries. These are fixed. Oh, I didn't write down this time what those even were. The box symbol represents the Planck length, Planck mass, Planck charge squared times by the coulomb squared. So we're normalizing that one, and we're normalizing this one, meter and kilogram. Just like we did here, using the relationship between the boundary and the projection, okay?
No, how did you come to that then?
How did I come to this? Oh, well,
I mean, that seems like an arbitrary thing. I mean, you must have had a clue.
the value of this is extremely close. Wow, that was terrible. Come on. To 10 to the negative 7. Extremely close. It's like 0.999999.
But
But
that's the assumed defined value of Ampere's constant.
Without the 4 pi, right? Yeah. So this is a famous constructive feature that people have known about, not just me, of course. The thing is, it was called upon when I noticed that we have a 2-part structure, and the second part of the structure shows up at the 7th digit. That's literally the only number I knew of from all my investigation constructed by the Planck constants themselves that characterize the 7th digit. And they almost do it exactly. That's really impressive. Okay, so that's a guess, right? We have 3 guesses here. We've got this structure, we're guessing that accurately characterizes the actual structure we found, but it's not a wild, bold guess. It's a guess that came out of looking first to see that that's there. Then we get this story of a quadratic structure that nails the fine structure constant, which we need for this piece to finish our story, but it comes with a bunch of other ones. So now we're going to take this base set of rules for the relationships between the roots, right? If the roots allow the transform, the symmetric transforms, these are the rules we want to check against. Check what against? Check this structure against. So we can look for J1s, J2s, J3s, and J4s here, not just J1s, okay? We can look for the rule set of the transforms there. What do I mean by that? All the partial sets. So this transform involves all 4 roots. It's the product of all 4. What do you get if you just take off the J4? What is it now? It's a partial transform, and it can't be 2 pi. It has to be 2 pi over J4, whatever that is, right? But you can take partial sets of these. So if you take the partial sets, meaning start with the first line, instead of taking all 4, I'm a partial, so I'm restricted to 3 or 2 sets. And it needs to be plural. So no 1 sets, just 2s or 3s, since there's only 4 there. So I can take J1 and J2. I can multiply them together and get a new answer and look to see what it is. If the answer is on the real axis, if it's a real number, then we're talking about a linear transform, the simplest kind of transforms a system can have. So those 2 together produce a linear transform. They're both real numbers. I haven't drawn them. Let's do that. So it's more easy to see what I'm saying there. Close to 0 is J1. Further out is J2. Up here is J3. And a mirror down here is J4. Okay, so these are complex. They have a value in the imaginary and the real axis. Right? They're exact opposites in that magnitude. And these are both real. Okay, so sometimes when you add 2 of them together or multiply 2 of them together, you get a complex output. Sometimes you get a real output. These two, this times this, gives you a number out here still on the line. This times this gives you a number out here still on the line because their imaginary parts cancel. Okay, so if we take the total sets of plural partial sets of these transforms and then check every constant of nature here for the partial sets, for any answer to come out. That's a lot to check now. We just really increased the checking set, right? You have to check against every partial set here, every partial set there, every partial set there. It's not an infinite set, but it did go up. Okay, that's what I did. That's the process. I found two rules. This one constructively built into the data points themselves. This one comes from the de Vries equation, and found that we can extend it simply with a very interesting relationship here, to get the right exchange. Now we're following and asking, can this quadratic structure give us relationships to all the rest of the transforms simply? If they do, we're going to take them more seriously. If we just can't find anything that simply relates them, we're going to say, all right, one of these two rules is wrong. We didn't make it. If we can capture the fine structure constant and whatever else it implies, right, if we have, then it gives us a very strong investigative tool to check the transforms against the actual structure. Okay, that's the process. I think the fastest I've ever said it.
Now, that there is one particular issue that I think you haven't covered yet that I could see that people would have questions of. Because if some of the best measurements, like the anomalous magnetic moment of the electron, if we have to 14 significant digits, and we only know those Planck dimensions to like about 5 to 7 digits,
thank you.
How are we going to scale this?
Thank you. Very, very good. You're absolutely right. There's no way you could get all the way to the end here without knowing how did we find values to use? How do we pick them? Earlier I told you in the investigation we picked all the possible ones. We took the digits we know are supposed to be right, and then just varied all the possible rest of the 14 digits and checked them all and put them in composite to see what happens. Okay, but we actually ended up landing on claims, right, for these values that give us exact geometric answers. So you can give 180 digits if you want, okay? Or you can give any number of specific digits, just not infinite. All right, how did we get there? We used basically the same process, right? We're using Wolfram alpha. We're taking the data point itself that's listed with its error bars, and we're checking for, and this took a while because we don't know what pattern we're checking against. We're checking for any pattern that then also extends to the others. So we got to find all the possible patterns, geometric relationships that could give us the number that we're looking for. And we don't know the way we're parsing the system to do it. So we have to check every way we can imagine the system parsing. And try to imagine more, honestly. So I ended up trying to settle on an exponential ansatz, meaning I want something that's exponential. I don't know what's exponential of, but there's an exponential in there. And a reason to suspect that is because this is an exponential system. So this wasn't the first thing I checked, but when I did check this, the system came out given as simple hyperbolic division structures that relate all four of them simply to the just hyperbolic sines and cosines. Okay, simple hyperbolic structures. And then we just took them seriously. We have exact claims and we can build constants of nature exactly from them. And if we can never get to a point where the pattern means something to us, then we have to backtrack and say, one of these is wrong, or this rule's wrong, or this rule's wrong. Something, one of the three things we're doing in this investigation. Okay, let me show what the actual values are we came to. The closed forms for them, right here. In each case, we have the number of degrees of freedom in the power of the base 10 exchange. We have an exponential ansatz raised to the number that they gave us, or the number in the data set, okay? And then we're set that equal to x and solving for something that can happen. Here's a geometric action, here's another one that actually gives us a value that spits out the right number here and here and here and here and here.
Okay. That's fantastic, but just, if this was my first time sitting here, I'm still like, how the heck did you get those numbers? Like, is there like a simple way to kind of go like, how did you actually calculate that?
How did I get the Planck values to begin with?
Basically, how did you go through? Because you're assuming some form of exponentiation. So
yeah, sure. Okay, let's run through one. I'll record the screen here. Okay, so well, first thing we need to do is we need to get the values. Number. There we go. 5.391247 plus or minus 60. 5.319247.
You had 319 previously.
Did I? Thank you. 5.3.
Oh yeah. Okay, yeah.
91?
Yeah.
That's why.
5.39.
Doesn't like. Now is it right?
Yeah, that looks better.
Good. Okay. Start over.
Oh, wait a second.
So far, this looks a hell of a lot better than what we've seen so far to me. Cool. So I want to check this guy. Pi sine squared 1/4. Let's see what it looks like. Pi times. It was sinh, right? Sinh 4th, and it was squared in the argument in text. All right. Doesn't mean much to me other than this type of plot, right? Okay, but if we make it richer so that we can see into it more, now it's a two-dimensional argument, so we're not just slicing it. Oh, I see a lot more structure. See how the complex map is altered? Okay. Cool. I'm seeing something here. A periodic structure, very looks like a regular manifolds we get from cosines and sines. All right, so this is how I did it. And then I picked this as the geometric action to inform us for the definition of this boundary. The fact that it's for a hyperbolic function, best thing we can have. Great. Same thing for all the rest of them. We search using the data point. We try to find some sort of hyperbolic function. We graph the functions. Let's look at the graphs of them. Here we go. Planck time, Planck length, charge, temperature, and mass end up having these graphs. We found functions that graph this way. And you might see a pattern. If you start from Planck time, look at the shape, jump to Planck mass. It's almost half of Planck time. Like you cut it right there and you flop that one down. Now it turned into this. And if you take this one and cut it down the middle again and flop one of them down, it kind of turned into that. It's like we divisions and we split in half, and flipped, but I'm kind of seeing that. These two are different, but these three look very, very similar in their entire shape. So this gives me more confidence that we're having a coherent system. We might be wrong, we might have an error anywhere. It's good to keep track of that, because if you can't get to the end where everything's put together, you have to be able to backtrack to where's most likely the error that I need to change, right? The pattern has come down to a set of 288 equations that are 36 equations from 8 rows. They divide up in 8 possible ways into these partial sets. Okay, there's 8 columns of partial sets here. 6 of them are Cartesian constructions and 2 of them are polar constructions, meaning they depend on radius and angle in their logic, and the other ones are actual XY. Okay, and the cool thing is when you look at the pattern yourself, you immediately see relationships between nearby neighbors. In fact, entire groups of them. And if you want to look at the entire set, you hit here, click on 288 on our website, you get the entire current list or poster. The first 2 columns here are just the relationships we found that are polar, and then the rest are the Cartesian. So column 3 is where we start the Cartesian relationships. A hyperbolic figure-8 knot can be thought of as a simple representation of a spinner. And if you want a bispinner, if you want to stack 2 of them on top of each other, then the simplest bispinner there is available to geometry is the hyperbolic figure-8 knot, which means we now have a geometry claim here saying that the electron's supposed to be a bispinner. And turns out we already know that was true. But we didn't get there from the same path. We didn't start there. This is just a geometric decomposition analysis, and it finds the same character. Now, the Gieseking constant, 2 times it, equals the hyperbolic figure-8 knot. So you could rewrite this as 4 Gieseking constants using 4 Planck mass boundaries divided by the kilogram cubed. Okay, so that's it. This is where we're at right now. And where are we trying to go? Why are we even doing this investigation? If we can figure out the decomposition structure of all the actual features that belong to atoms and the transforms available to atoms, if we literally figure them out, it means we know we can logically encode them. If we can logically encode them, we can take advantage of them on purpose like we do on computers when we code a system to do something that would take lots of steps, but you want to do it millions of times. So we want to investigate that structure to such precision that we can actually then figure out how to constructively on purpose make the transforms, or the sequence of transforms happen to make the things we want to make. So this is going to dovetail. Echelon's been spending many, many years trying to think about how to write code that actually conforms perfectly, or as perfectly as possible. It keeps getting better and better to just the laws of physics, right? Just to see what you can build when you start from laws of physics and let play. my end goal is to end up understanding the complete computer program we build using just transform logic of physics and actually physically make one, right? One of his goals is to make a replicator that's, what do you call it, the more advanced AI that physically builds things with 3D, and you can make it just go out there and start building things, yeah. But AI-wise, that's a version of replication, right? That's more advanced than what we got right now. And I want to do this form, I'm imagining much closer to the Star Trek version, gives you something on the wall just to say, I want dinner, and I want it to be hot turkey dinner, and there it is. To get there though, we have to actually, someone has to constructively understand all of the features and how they fit together in physics, right? I mean, humans have to get to that point. So we've separated all the parts, we found the pattern in the parts. What I want to do is fit the parts all together, right? I want to literally get one geometry in which you can show the transform of that geometry separated into all its individual transforms, like a Rubik's Cube. I can twist it this way, I can twist it this way, I can twist it this way, I can show me all the ways we can twist it, and it comes back to itself. Those are all the symmetric transforms that are available to it. And each of the constants in nature should literally characterize one of those. So far, this method, especially this quadratic form, has allowed me to look in much, much, much richer. When we did, the pattern came out, like rich, unavoidable, beautiful pattern, and we kept trying to squeeze it down until that pattern literally conformed to the smallest set of inputs. And it's just these 5 bases and boundaries, and everything else builds from them. It's a very exciting way to try to make sense of things, an algebraic geometric decomposition of the structure. Now we need to go from that understanding to the geometric fitting together of the transforms, but also the next step is how to code all of those transforms. Right? If you can figure out how geometrically to fit them together, that is kind of coding them already. So that's what I want to do. That's where we're at, and what do you guys want to ask about? Oh, hey Rick.
Hello. I've been really like salivating over what you've been doing. Everything you're doing, Thad, makes sense. So I'm quite enthusiastic about what I saw. Everything that I saw just now on the whiteboard, like, yeah, that's rock solid. Let's go with that. And your story, I noticed, is not changing. You don't go in and like modify things. You like put a new discovery in once in a while, or you adjust a constant. But the basic ontology, shall we say, of the different formulas you're using, they're not changing. You're staying inside your model, and that's a really excellent indication that.
Well, the fact that I can is really excellent. Yeah.
We're gonna have a couple of sessions throughout like the next week and stuff as people are here. Did you have any particular questions or additional comments on what we've seen so far?
Mostly, I'm just like hello. I'm really glad to be here, Thad. You just laid out everything very, very clearly. And let's keep going on this this model.
Cool. Thanks, Rick.
Thank you, sir.
So since this investigation ended up telling us that it looks like the story of the geometry here, it's centered around this Gieseking manifold that's double covered into the hyperbolic figure 8 knot, we should look a little bit into hyperbolic figure 8 knot. What is its structure? What do we know about it? Turns out this is the constructive equation for the hyperbolic figure 8 knot. It's made up of 2 diagonal logarithms. 1 over the imaginary golden ratio is the first argument. Next logarithm is just the imaginary golden ratio. Now, I equals -1 to the 1/2. Imaginary golden ratio equals -1 to the 1/3. I bring this up because I'm saying this structure itself is unitary. The magnitude of I is 1. The magnitude of the imaginary golden ratio is 1. They're all in the unit circle. So this is a unitary construction to begin with. Beautiful. But it has 1 unit, 2 units, 3 units, 4 units. It has 4 units it's putting together. Okay? Next step. If we look for the real conjugate of this same structure, so we're just trying to ask, what are the positive piece? If instead of taking the difference between them, we're going to take the sum. Then this tells us this is our hyperbolic figure eight knot is a loop you put on the surface of a sphere, but it actually has crossings. In four-dimensional space, it's just a loop on the sphere, though. And here, we're going to get our projection, or our complement of a hyperbolic figure eight knot, and it is or you could write it as 4 pi squared over 288. It divides up into 288 ways. What this means is this is a system that defines a metric from which there are 288 independent equivalent ways to derive the structure of the metric. There's 288 bases from which the structure could be set, and you get all the same rules no matter which one you set. Okay, but there are different ways to structure the system, but they get you the same place. So fantastic. There's a symmetry in the system itself based on the 288. Another one was figuring out this structure inside. If we split these up and look at just this first piece, they actually are complex things, right? You might imagine this one's I is right here, and imaginary golden ratio is right there. So it's complex, right? The complex value for this one, make sure you get the sign right. 1 over, negative 4 pi over 24 squared minus the Gieseking constant times I. The other one, this one, is the same thing, but plus. So when they combine, these pieces go away. Well, if you combine them the right way, these pieces go away this way, and we get this and another one of these, and the I and negative go away, we get 2 GGI. Okay? But we can combine them the opposite way and just get structures in 4 pi's. Okay. So this, yeah, go ahead.
Well, so is there anything interesting or perhaps useful aside from it just being a very useful thing? Like, is that equivalent to anything else volume-wise?
Yes. Well, we can also say if you have the same structure, let's start with just this first equation. We have it, and we only have its components. We only have dilogarithms, we only have i's, ones, and imaginary golden ratios. You can set the same thing to the other available argument there. And now instead of being 2 GGI, it's 2 times Catalan's constant. I'm using K for Catalan's constant. That's not a universal thing. Some people do it. Some people use G. Some people use C. It's not very consistent, but I'm saying Catalan constant's capital K. Okay, so we have a Gieseking and Catalan construction. They're the same logical system. We're just looking at the same logical system, dividing it in 90 degrees, or dividing it into a third of a flip, a third of 180 degrees. Okay?
So can't, isn't the figure 8 constructed from Adrian?
Yes.
Oh,
The figure eight is
the
constructed
simplest
from
platonic
two
solid.
The simplest platonic solid, which is very fascinating. So the base construction is made out of 2 copies of the simplest platonic solid. They're opposite pointing, but yes. Anything else? Okay. Lunch break,
Cool.
and then Echelon's going next? Cool.